All right, the water issues from a hole in the side of a tank. Excuse me, the water issues. Gesundheit. Okay, oh, I'm sorry. In the side of a tank at 18 meters per second. So here's this tank, the shape of which is not super important, right? And there's a hole in the side, and the water's shooting out here at 18 meters per second. And we want to know what this height is, right? So there's this water in there, right? And we've got the density of the water and all this stuff, right? And so basically, this is situation 1, this is situation 2, right? So P1 plus rho GH1 plus, I know they use a Z plus 1/2 rho V1 squared is equal to pressure 2 plus rho GH2 plus 1/2 rho V2 squared. Now, the pressure here and the pressure here, like outside, are the same. So the height of situation 2 is 0. H2 is 0. So this term goes away. We don't want this term to go away, right? Because we're trying to solve for some velocity here, right? And then the question is, how big is this tank, right? Let's assume that this tank is very large. Okay, then it's the velocity 1 is essentially 0, right? So then we get rho GH is 1/2 rho V squared, right? So rho GH is equal to 1/2 rho V squared down here, right? This V2, right? All right, so, oh, do you notice the rows cancel? That's kind of fun, right? All right, so 9.81 times the height is 1/2 18 squared. We can do this. We can do it. 0.5 times 18 squared divided by 9.81 is 16.5 meters. Ta-da, right? This is, of course, Torricelli's theorem. I was trying to resist not writing that down. But if you solve this thing for V, you get square root of 2GH, which is, incidentally, that's the speed that a rock would have if you dropped it from this height. When it reached here, it would be going, whoops, that's supposed to be little. It's supposed to look like that, right? At that point, it would have exactly a speed of 18 meters per second because of energy and stuff.